look at a blood vessel. A blood vessel is kind of like a tube, I think you'll agree with me. It's a tube through which blood travels. So here I'm drawing a tube, and I'm going to ask you a question, which is, what makes up the walls of this tube? Now for a blood vessel, what makes it up is something called an endothelial cell. So actually the walls are made up of these kind of gooey endothelial cells that are stuck together tightly and that together form a tube through which the blood will travel. So here I'm drawing a bunch of cells tightly stuck together. They're stuck together tightly to prevent blood from coming out, of course. So this is more or less what it looks like. Each of these is a cell, and so of course each one has a nucleus, which I'll just quickly draw like that. Now let's delete that and let's change views to something a little bit easier. So now here is the same blood vessel in cross-section, and so these are the endothelial cells which we're seeing in cross-section, and maybe here we can draw the nucleus of this one. Maybe it's visible right there. So now we have blood moving through this blood vessel. Here are some red blood cells, and they're moving along, providing the body with oxygen. But a very important question to ask is, what happens if this blood vessel gets damaged? So let's say that those two cells right there split open and they break open. What's going to happen if we don't fix this is that all of our blood is just going to rush out here and we're going to lose blood. So what is your body going to do about this? Well, it's going to use a special player that we haven't talked about yet, which is the platelet. So I'm drawing a platelet here, and a platelet is basically a tiny piece of a cell. It doesn't have a nucleus or anything. It's a tiny little piece of a cell that your body uses to block up holes like this. So you have them floating around in your blood all the time. Here I'm drawing a bunch. And what happens is when you have a hole in your blood vessel, they're going to come together, they're going to stick together, and they're going to clog up this hole. And so basically they've built a little barrier so that we won't keep losing all our blood. So are you satisfied? Well, you shouldn't really be satisfied, because there's a big question here, which is, why are these platelets clumping here? And why aren't they clumping, for example, up here? Why don't they clump there? Or maybe even just in circulation, why don't they clump up like this? Because if what they do is to clump up, how would they know to clump up here and not here? What's telling them? So these are things that we don't want to happen, so I'm going to put a little X through them. And the solution to this problem is actually quite simple and beautiful. The point is that the environment in the blood vessel is different from the environment outside of the blood vessel. So outside we have some things that we don't have inside, and one of those things I'm going to draw here. I'm drawing it here, and it has a name. It's called collagen. So I'll write that down here. It's called collagen. You don't have to worry too much about what it is. Collagen is kind of a structural protein that your body uses to give structure to things. And so the important thing is you have collagen down here, and you don't have it here, you don't have it here, you don't have it here. And it turns out that collagen chemically interacts with the platelets, and maybe we'll draw a little spark there to show that they're chemically interacting. It chemically interacts with them and causes them to stick together and form this plug that we're talking about. So we can call this, by the way, a platelet plug, because it's plugging the hole. And by the way, just to be clear, you also have collagen up here and over here. So it's basically everywhere outside the blood vessels. Now it turns out that this is only step one of the clotting mechanism of your body. So up here we'll put number 1, platelet plug. And there's actually 2 steps, because the platelet plug itself is not quite as strong as we would like it to be. So there's a second step which makes this plug stronger. And that second step involves something called fibrin. So we'll write that here, fibrin. And fibrin is not a little mini cell like platelets are, or a fragment of a cell like platelets are. Fibrin is just a protein, And what fibrin is going to do is it's going to come here and it's going to try to strengthen this plug by forming this mesh of protein that's going to hold all these platelets together and form a very tight object. Now these fibrin strands, that's what each of these little squiggles is, it's a fibrin strand. These fibrin strands are made up of little fibrin subunits, which I'll draw here. And it turns out that these subunits naturally like to come and stick together. And I guess the technical word for this is they polymerize, they form a polymer. Basically they just stick together, and lots of them will stick together in a line to give you this fibrin strand we see here. And where does this fibrin come from? Does it come from down here? No, it actually also circulates in the blood. So let's draw some little fibrin molecules up here. So they're circulating in the blood. Is this right? Well, this actually can't be exactly right, because I just told you that these fibrin molecules naturally stick together. And so if we had these fibrin molecules circulating in the blood like this, what would happen? Well, they would actually stick together in the blood. And they would form these long strands in the blood that we didn't want, because we only want the strands here at the platelet plug. So let me remove those strands. So it turns out that we don't have fibrin circulating in the blood. What we have is something slightly different. We have fibrinogen. Fibrinogen. And so I'll draw a fibrinogen down here. Of course, keep in mind these are all my little cartoons, and probably it doesn't look like this. So these guys we said were fibrin. Fibrin. But now this molecule is a fibrinogen. And you'll notice it's the same as a fibrin, except it has an added little piece to it. And that little piece, as you can tell, is going to keep it from sticking to itself. These fibrinogen are not going to be able to stick together the way that these fibrin are. So what do we need to do then? Well, of course, we need to turn this fibrinogen into fibrin. But where are we going to do that? Only at the site where we want fibrin strands to gather. So only here, where we have that damage. And so again, we face the same question that we faced with the platelets, which was, how do the platelets know to aggregate here? Well, likewise, we want to know, how do the fibrinogen know to turn into fibrin here so that they can then stick together and form the strands? And the answer basically is, luckily, the same. So we have some chemicals down here. Now we're not talking about collagen anymore, we're talking about something else. And if you really want to know what it is, I'll write the name here, but it's not really the name that's important, it's the principle here. So the principle is you have these little proteins down here called tissue factor, and they're normally not in the blood. They're only down here outside of the endothelial cells lining the blood vessel. And so these little proteins, tissue factors, are going to be right here in this little wound and around the wound, and there they'll cause these fibrinogen to become little fibrin protein molecules, and then those fibrin will be able to stick together, and they also stick to the platelets, by the way, I hope I was clear about that, and form the mesh that we see there. Now if we want to get really fancy, we can ask, how does tissue factor turn fibrinogen into fibrin? And you can ask, is tissue factor kind of like a little knife? Is it, and by knife I really mean enzyme, is it a little knife or enzyme that causes this piece to break off of the fibrin so that we're left with just fibrin? And actually, unfortunately, the story is much more complicated than that. And there's actually a good reason for it. Because let me propose to you a situation. Let's say you have to turn 1,000,000 fibrinogen into fibrin. Because each of these fibrinogen is a very small protein, so we need about 1,000,000 of them to make up this clot here. And let's say that you are tissue factor. So you are tissue factor, and you want to turn 1,000,000 fibrinogen into fibrin. Is the best way to do it for you to actually sit down and chop off this piece off of all these fibrinogen, one by one? That would take you a long time. Is that better, or is it better for you, as tissue factor, to call up 5 friends? And have each of those friends call up 5 friends. And have each of those friends call up 5 friends. And keep doing that until you have a huge number of people there ready to help you. And now get all of those people to help you convert fibrinogen to fibrin. So obviously that latter scenario is a more efficient mechanism. And so that's what your body does, and that's what tissue factor does. So tissue factor, and by the way, I know this is getting convoluted, but try to stick with me. Tissue factor is going to turn another protein that we haven't talked about into its active form. And then that other active form of that protein that we haven't talked about is going to activate another protein that we haven't talked about into its active form. And then that one is going to do the same, and then that one is going to do the same. And so basically every time you introduce a new protein there, you're ramping up the total number of activated proteins of that type. And so finally, by the time you get to the one that's going to break the fibrinogen apart and create fibrin, and by the way, I'll draw him, and he has a special name called thrombin. Again, I don't think thrombin is necessarily a word you need to know, but just in case. So by the time you get to thrombin, you have a lot more activated thrombin than you had tissue factor in the beginning. But the tissue factor here is the spark, and that's the guy that really got us going. So that's basically it. This is how your body plugs holes in blood vessels and keeps you from losing too much blood. And if you want to know more about that kind of complicated stuff I said at the end about, all these different levels of activated proteins, you can look it up. It's called the coagulation cascade. It's called a cascade because you're cascading through all these different levels of proteins.